Hello. Hello.
Good morning, sir.
Yeah, good morning. So am I audible?
Yes, sir. Yes, sir.
Okay. Could I able to see the slides?
Yes, sir.
Okay, very good. So any questions regarding the previous class on sand drains? Anybody will like to pose a question or get clarified the sand drain technology? Anybody has any question? Okay, so no problem. So let me start the today's lecture. Uh, in the previous class, we were discussing about the sand drain technology. So this is one of the ground improvement techniques of clay soil, especially. So these are some typical features of the sand drain technology. The diameter varies from 150 to 500 millimeter. So the sand drain is created by making a hole to the ground and filling it with the sand. Now, when you fill the sand into the clay material, so there is a contrast in the permeability value between the native soil and the sand that has been filled. So this contrast in the permeability creates the gradient in terms of the permeability and thereby accelerates the consolidation process. So in a nutshell, we can understand that. So when you go for the sand drain technology, you are doing a couple of the fundamental things are, first thing is you are creating a kind of a gradient for accelerating the permeability and thereby the consolidation. Second thing, you are shortening the path traveled by water molecules. So these are the two fundamental mechanisms by which sand drain technology works. So for installation of the sand drain, we can go for any one of these techniques for making a hole. Either you can go for the driving, jetting or rotary drilling depending upon the soil type and availability of the equipment at the site. The typical spacing of sand drain varies from 1.5 to 4.5 meter, but 4.5 is very odd. The typical is 1.5 to up to 2.5 meter. The working depth is 30 meter to 35 meter. So once all the sand drains has been installed on a given area, so then all these the surface of the site is covered with a sand blanket whose permeability is also very high. The approximate thickness of this blanket layer is 0.6 to 1 meter. So then there are some important points and the limitations also we did discuss. Suppose if the diameter of the sand drain is too large, then it may tend to act like a weak pile. So however, the core function of the sand drain is to squeeze out the water by accelerating the consolidation. It's supposed not to take any amount of the axial load from the superstructure or the free load, the surcharge load. So therefore, you need to be a little bit cautious when you try to decide the diameter of the sand drain. By no means it should act as a weak file or it should take any kind of a load. So this is some information about the drain backfill material. It should have sufficient permeability. So the permeability should be almost as per some guidelines. The contrast in the permeability between the sand and the clay should be at least 1000 times. And the backfill that you are going to use for filling purpose should not have more than 3% by weight of the fine particles which are passing through sieve number 75 microns. So here enlisted a couple of the factors which can affect the performance of a sand drain, which includes drain effects, smear disturbance, well resistance, loading rate, creep effects, hydraulic flow formation. So, and these are some limitations of the sand drain technology. Sand drains are ineffective in controlling the secondary consolidation for highly plastic and inorganic soil. I also explained the reason behind why the sand drains are ineffective for the secondary. When you talk about the consolidation, primary consolidation basically attributed to expulsion of water from the pore voids, while the secondary consolidation is attributed to expulsion of water within the diffuser double layer. But when you apply the surcharge load, it is a mechanical loading condition that could able to expel only the water from pore voids. So it is ineffective on the water held by the electrochemical forces, that is diffuser double layer. So since it is ineffective in expulsion of water from the diffuser double layer, so therefore it is ineffective for secondary consolidation. So effectiveness of sand drains did not take into account the excess pore water pressure developed, which tend to act as a weak piles that reduces the strength in the clay. So in fact, when you apply the surcharge load, it immediately develops the excess pore water pressure. And these are some factors. We will elaborately discuss about each and every factor, how they are going to affect the overall drain efficiency. In a nutshell, you try to understand how many number of factors that could able to affect. So first of all, there is a clay. So there is a clayey material and there is a sand drain. So when you want to install a sand drain or when you want to create a sand drain, you need to make a borehole. So when you are making the borehole, so it is certain that you are going to create some kind of a disturbance to the walls of the borewell. Suppose if you look at this diagram, so here it schematically explains what kind of disturbance that can cause and how much it will be. You look at the bottom right side diagram. So this is you can say a well. So at the center is the bore well and followed by, so this is the vertical drain, and here you can see there are some disturbed zones and undisturbed zones. So this small hatched portion, so right adjacent to the drain, indicates this is the zone of influence of the soil and outside is undisturbed soil. So when you make any drain or when you make any borehole, so you are going to create some kind of a disturbance right adjacent to the borehole wall. So there is a drain and there is a disturbed soil and there is a undisturbed soil. The drain is filled with the sand, so the permeability of the sand is a different value and the permeability of the disturbed soil is a different value and the permeability of the undisturbed soil is a different value. So overall you have a 3 zones and 3 permeability values. So this is one thing. The zone which is under disturbed state is called as a smear zone. So smearing means it's applying some kind of a what do you call coating, some kind of coating. Here when the mandrel is inserted into the ground, it is going to cause some kind of disturbance to a small diameter, a small radius. So here this hatched portion. Now when there is a disturbance, it is obviously going to affect its permeability value as compared with the native clay soil. So here the permeability of the clay is different than, though this is called as a smear zone. So the permeability of the smear zone is different than the permeability of the original clay material, and sand permeability is different. So smear zone means a zone created so during the insertion of the mandrel into the clay soil. So usually the diameter of the smear zone is very small, as you can see. If you make a comparison, so this is a undisturbed soil and this is a very small zone that is called as a smear zone. Now although I told the permeability is contrast in the smear zone, usually the permeability of this smear zone is little lesser than the permeability of the original clay. So this is the reason. So the water might penetrate from this location to this location up to smear zone. For example, so this is undisturbed zone. The water molecule may travel from this location all the way to up to smear zone, but the permeability of the smear zone is slightly lesser than the permeability of the original soil. So therefore, it can create some kind of a impediment to permeability. So that is called as a smear zone effect. So this picture gives further details. So this is RW is a radius of the well, KS is permeability of the smear zone, KH and KV are the permeability in the horizontal and vertical direction of the original clay. So these are cross-sectional diagrams and the plan view. So to understand the differences of disturbed zone and undisturbed zone. So this is further elaboration. Both are same. So these are some possible failures with regard to the sand drains. As we can see, the first one is break in continuity of the sand drain. If the soil is too soft, as we can see, if the soil is too soft, it couldn't able to provide any kind of a lateral support. If there was no lateral support at all, then because of the gravitational effect, there may be some discontinuity, because too soft means it is almost like a slurry. So this slurry couldn't able to provide any kind of the lateral support. If there was no lateral support at all, there is a possibility of discontinuity of the sand drain from top to bottom. Then another possibility of the failure is damage of advanced sand drains by next installation. As you can see, if you not properly design the spacing of the sand drains, when you are installing the adjacent one, so it may cause damage to the adjacent sand drains. So because of the lateral thrust. The third possible failure is deformation and damage of sand drains during the piling embankment. So you can see after you have put the surcharge load. So because of this surcharge load, there could be development of the lateral thrust, and that may exert the thrust in the lateral direction on the adjacent sand drains. So causing the failure of the soil as well as the sand drains. Then the zigzag formation of sand drains by large settlement. If you do not anticipate too much amount of settlement, because the settlement will occur within the clayey soil, but at the same time the sand drains also has to undergo the settlement, so in toto with the original soil, okay, which otherwise they could be able to taking the load, which suppose not to happen. So in order to avoid that, so the sand drains also undergo the consolidation process, but during the consolidation process they can bend in different forms. These are called as the kinkings. So if these bends are too much, then they may affect the permeability, so which is very danger. So when there is an effect to the permeability, then it obviously reflects or its effect on overall performance of the sand drain. So these are a possible causes of the failure. So you have to give some kind of importance to these aspects when you design any sand drain. So these are some important points to be kept in your mind. Sand drains are constructed either in a triangular or square pattern. The permeability of graded sand should be at least 1000 times more than the permeability of the consolidating clay. The spacing depends on type and permeability of soil, and it must be less than the thickness of the clay layer. Consolidation time is mainly affected by the drain spacing rather than the drain diameter. So although both spacing and diameter affects, but the spacing is more prominent than the diameter. The efficiency of the sand drain mainly depends on correct estimation of the coefficient of consolidation in horizontal and vertical direction. Then usually CH is greater than CV. This is because the permeability in the horizontal direction is greater than the vertical direction. Hence, higher the ratio of CH by CV, more effect is working on sand drain. So these are a few important points, so to be kept in mind when you design any sand drain technology. So that's what all about the sand drain. So let us come to the theory of the consolidation. You have already seen the theory of the consolidation, that was a one-day consolidation. But when you talk about the sand rains, it is the three-dimensional consolidation. So these are some governing equations and their analytical forms. So this is the equation that you have dealt during your one-day consolidation. CV into dou square u by dou z square is equals to dou u by dou t. So the dou u by dou t means this is the rate of change of pore water pressure with time. So rate of change of pore water pressure. And if you look at the radial flow, so this is a function of both. So the change in pore water pressure as a function of the time and the change in pore water pressure as a radial distance. So R is the radius of the well, the radius of the well. So these are the two governing equations when you consider vertical flow alone and when you consider radial flow alone. In fact, and no, it's not showing anything. Okay. There are some formatting issues. Let me see. Yeah, you can see these are the form of equations. We have seen the CV. So the equation of the CV, the coefficient of consolidation in the vertical direction, CV is equals to TV into H square by T, or a rearrangement of the same thing in different forms. CV is equals to KV into 1 plus E naught by AV into gamma W. AV is also the volume compressibility of the consolidation, and this can be rearranged in this form. The additional term that comes into the picture when you talk about the sand rains is the coefficient of consolidation in the horizontal direction. So these are the form of equations. So this is with respect to vertical consolidation and this is with respect to horizontal consolidation. So if you look at carefully, so here H is the thickness of the layer, but in the vertical direction. DE is the radial distance, that is you can say here the zone of diameter of the zone of influence, but in the lateral direction. H is in the vertical direction, so DE in the lateral direction. So that's what is the distinction between the vertical consolidation and the radial consolidation. So these are other the consolidation forms. MV is equal to AV by 1 plus E naught. Coefficient of volume consolidation, coefficient of volume compressibility, so on and so forth. So where DE is can also be written in the form of 2 times of R, where R is the radius of the zone of influence. And TR is it's a time factor for radial consolidation, so that can be written as CH into T by 4R square. So if you compare the time factor equation for the radial consolidation with that of vertical one, so in case of the vertical one, the H is taken into account, that is the thickness in the vertical direction, while in the case of radial, so it is R, that is radius of the zone of influence. So there are other equations. The degree of consolidation, also referred to the rate of consolidation, is defined as this one, U naught minus UT by U naught. So U naught minus UT means the change in pore water pressure divided by the initial pore water pressure. U naught is initial excess pore water pressure, UT is remaining excess pore water pressure at time t. So if you deduct initial minus final, this is nothing but the change in pore water pressure and divided by U naught. So usually we always try to correlate the degree of consolidation with the dissipation of the excess pore water pressure. And the UR and UV, so these are the two additional terms. UV is nothing but the average degree of consolidation in the vertical direction, and UR is with respect to the radial consolidation. So UR is a function of the TR, time factor, in the radial direction. UV is time factor in the vertical direction. And the overall degree of consolidation is calculated by relating with the both the degree of consolidation with respect to vertical and with respect to radial. So 1 minus u is equals to 1 minus uv into 1 minus ur. So u is overall degree of consolidation, uv is vertical degree of consolidation, ur is with respect to radial consolidation. So in case of the radial consolidation, one of the most important factors is how much time it required to consolidate or to achieve the consolidation of 90%. So this is the equation, you can use it. So time required for achieving the desired degree of consolidation. So this is a T and this is UR. So time required. So this is a T and this is UR, but this is only related to the radial consolidation. So you can fix the target value of the radial consolidation and you can calculate how much time approximately requires to achieve this degree of consolidation. And of course, this time is a function of the zone of influence, and this is a factor. So I will explain about this factor in the subsequent slides. And CH is the coefficient of consolidation in the horizontal direction. Now, where mu is a F, just recall in one of the slides I was talking about different factors that can affect the performance of the sand drain, like a smear effect, well resistance, drainage characteristics, so on and so forth. So this mu accounts for all those things. Like if there is a smear effect, then how the overall degree of performance is going to be affected. If there is a well resistance, and how it is further going to be affected. So can only smear affect the performance, or smear plus well resistance both can affect the performance. So these are the few things we will look into it in the subsequent slides.
Sir, the diameter of influence which you are telling includes the smear zone or not?
Yeah, it includes the smear zone.
Okay.
Again, some formatting issues. So this is the equation for mu, so that we were discussing the previous slide. So here there are other terminology also. QW is the discharge capacity of the drain. The permeability of the soil is Kc. Z is the thickness of the layer, and L is also thickness, but there is a small distinction as you can see. L is length of the drain when open at one end only, half the length of the drain when open at both the ends. Z is distance from open end of the drain. So these are the distinctions. When you solve the problems, you can understand how to distinguish between L and Z. Then N. So N is the ratio between drain diameter to zone of influence. So there are some importance. When QW by Kc, QW means the discharge capacity of the drain by the Kc, that is permeability of the soil, is less than 3000 meters square. Well resistance cannot be ignored. So well resistance means, so this is typically related with the drainage properties of the material. So I was discussing about the smear zone. So this is a small thin layer of the soil disturbed right adjacent to the borehole wall. But there are other properties, like if you look at the original clay soil, there the permeability value is not constant. And when you apply the surcharge load, so because of the surcharge effect, there is a changes in the drainage properties of even native soil also. So that all comes under well resistance. So when there is a disturbance to the soil, how it is going to affect the performance of the sand drain. If there is a changes in the drainage properties, then how it is going to affect the properties, the overall performance of the sand drain. So this is this equation is accounts for well resistance. So accounts for well resistance. Well resistance is typically attributed to the drainage properties. So this is this equation which accounts for the well resistance and the smear disturbance. So smear disturbance means, as I told, a small zone of the soil, a very thin layer of the soil getting disturbed during the penetration of a mandrel. So when there is a change, there is also change in the permeability value. So that permeability is accounted for as Kc dash, as you can see here. So Kc is the permeability of original clay. Kc dash is permeability of the disturbed zone. So this is these are the this is a big equation. So you don't need to remember these equations. Only one equation, simple ones, but you don't need to remember this equation. In fact, this equation accounts for both smear and well resistance. Yeah, well, I don't know. Okay, so this is the equation for accounting for the smear effect. And there are some other terminology. Here there are two terminology. One is N, next is S. So N is the, suppose if you look at this one, N is defined as the diameter of the well by the diameter of the zone of influence. S is defined as the diameter of the smear zone divided by the diameter of the well. So where ds is diameter of the disturbed zone. And dw, so this is the equation used in case of the PVD, not in case of the sand drain. So this is used for the PVD, that is prefabricated vertical drain. So that I will discuss either today's class or next class. So these are other equations, consolidation due to vertical flow. So I will not elaborate anything because these equations are very well known to you during your undergraduate program. So Terzaghi very well talked about 1D consolidation. So this is Terzaghi's theory of 1D consolidation. So where we have seen the time factor in the vertical direction, that is TV is equals to 5/4 into UV square. So this is the relationship between time factor to the average degree of consolidation in the vertical direction. And depending upon the degree of consolidation, so the pi/4 into U square is valid for the average degree of consolidation from 0 to 52.6. I think earlier it was written up to 60%, but make a correction, it is valid up to 52.6%. So if the average degree of consolidation exceeds this value, then we have to use another equation to compute the time factor, that is TV is equals to 1.781 minus 0.933 log base 10 100 minus UV. So only distinction is you might have read the validity of these two form of equations between degree of consolidation above 60 and below 60, but make it correction to 52.6. So then alternatively, you can use this predefined chart to pick up. So if the time factor is calculated, then what would be the value of the degree of consolidation in the vertical direction? Or alternatively, so if I know the degree of consolidation, then I can pick up the value of the time factor, that is TV. So several people did work on to provide the analytical solutions for three-dimensional consolidation. One of the very earlier person who did work on the sand drains is Barron. So Barron is the first person to provide analytical solutions for calculating the degree of consolidation based on the sand drain technology. So he considered equal strain consolidation with no smear effect. That means no disturbance to the soil mass. So everything works as it is. And the surcharge load is applied instantaneously, as you can see here, although it is practically not possible, but this is an assumption. So the Barron has proposed the equation for average degree of consolidation due to only radial drainage. UR is equals to, so this is the analytical equation if you solve the governing equation of the radial consolidation. So UR is equals to 1 minus E into minus 8 TR by f of n. So E is exponential function, f of n is a function, so which is defined as n square by n square minus 1 into log base E of n minus 3n square minus 1 by 4n square. So where n is defined as the radius of the zone of influence divided by the radius of the well. So this is Barron's contribution. So he proposed the equation in the year 1948. But only limitation is that the Barron's equation doesn't account for the smear as well as well resistance. So this is some free defined chart provided by the Barron. This is very similar to that chart which we have seen between TV versus, but there was no sand rain, so therefore it was a single curve. But when you talk about the sand rains, so we can provide a variety of the sand rain diameters, and accordingly for each sand rain diameter there is a different zone of influence. So therefore we need to embed another parameter, that is n, which is the ratio of the zone of influence by the diameter of the drain. So accordingly a free defined chart has been developed between UR, average degree of consolidation due to the radial drainage, versus TR, time factor because of the lateral drainage, as a function of the n, as you can see here. So if you look at this graph, so it says that this graph is valid for different drain diameters and different zones of influence. So that's what is the beauty of this predefined chart, which was not the requirement in case of 1D consolidation. And the same chart in numerical value form. So these are the tabulated values. Either you can use the previous chart or you can use this table. Both will give you the same value. And the Barron's equation was modified further to account for the smear zone and the radial consolidation. So here, but this is for radial consolidation. So this is the factor U, so which accounts for everything. For example, this is the big equation. Again, I repeat, you don't need to remember these equations. This is 1 by m dash into U average degree of average pore water pressure, minus R by RE. So R is the diameter radius of the zone, and this is the radius of the zone of influence. RS is the radius of the smear zone. KH is the permeability in the horizontal direction. KS is permeability of the smear zone. N is the ratio of the zone of influence by the drain diameter. S is the zone diameter by the borehole diameter or drain diameter. So this equation accounts for both smear effect as well as well resistance. So these are further definitions. As you can see, S, capital S, the radius of the smear zone by the radius of the well. There is another factor, that is m dash. So this is a big equation of m dash. Then U average. So this is U average. So U average is nothing but UI into exponential minus 8 TR by m dash I. So average degree of the average pore water pressure is related to the time factor m, and the average degree of consolidation with the smear effect is given by UR is equals to 1 minus U average by initial pore water pressure. So the same thing can be expressed as in this form, just a replacement. Okay, so if you look at these equations carefully, the average degree of consolidation can be calculated based on by measuring the pore water pressure. So for that you need to monitor, you need to have a monitoring mechanism constantly how the pore water pressure is dissipated from the initial pore water pressure condition. Or the other way around is you try to calculate the time factors and correlate with the degree of consolidation, the way we have done it in the 1D consolidation. So these are for different conditions. There are two variety of loading conditions has been given here. First is applied instantaneously. This is an assumption. Practically, it is not possible. The second thing is this is improvement over the instantaneous condition and ramp loading. As you can see, the loading is applied as a function of the time and thereafter it became a constant. Now these assumptions are required to provide analytical solutions for the governing equations. And accordingly, you can see these are the solutions provided for different loading conditions for instantaneous and for ramp loading. So if you compare instantaneous with the ramp, so the ramp loading is more practicable and that realistic. So instantaneous is practically not possible. And these are some the solutions of analytical equations for both the conditions. Same thing for instantaneous application of the surcharge, equation for time factor, for degree of consolidation it is 52.6, and equations for ramp loading, so for different time conditions up to application of the load and for constant load. So these are predefined chart to pick up the values of the degree of consolidation as a function of the time factor. So there are several persons who did work on the sand rails. So as I told, Barron was the very first person, but thereafter his equations was refined further to account for the smear effect as well as the well resistance. So Hans Boy is one such person who provided the analytical solutions accounting for the smear and well resistance. So these are the equations. So there was no change in analytical form of the degree of consolidation, that is UR is equals to 1 minus e power minus 8 TR by mu. So where TR is the time factor due to radial dryness, that is CH into T by dE square, and mu is a constant factor which either accounts for only the smear effect or smear and well resistance. So this big equation accounts for both smear as well as well resistance. So these are this Hans-Boy equation is widely used equation with and without accounting for smear and as well as well resistance. So mu is equals to ln. We have also seen this kind of equation. So in the previous slide also. So but the Hans-Boy equation is very familiar as compared with any other thing. And these are the definitions of the different terminology. And you can see all the parameters has been defined here. So the same Hans-Boy equation, now they have further segregated to account for only the smear effect and to account for only the drain effect. So if you want to account only the smear without well resistance, the same form of equation, this was modified to ln n by s plus kh by kw into ln s minus 0.75. And in case if it is a perfect dry, there was no effect, nothing, no smear effect, no well resistance, then f is nothing but ln n minus 0.75, only the ratio of Re by Rw. So there is some observations by the different people. For example, in case if Re by Rw is greater than 5, the free strain and equal strain solutions give approximately the same results for the average degree of consolidation. So this was one of the important observation. So if you look at these equations, another thing also you can understand. A few people have considered the free strain condition while some other has considered the equal strain condition for deriving the analytical solutions for the three-dimensional consolidation. So this already we did discuss. Once we know UV value and UR value, then how to calculate the overall degree of consolidation. Then how to calculate the time required for desired degree of consolidation. So these two form of equations we have seen. Now a couple of unknown factors in the previously shown equations are the S, the radius of the zone of influence, so on and so forth. So when you talk about the zone of influence, so that is capital R. And we also did discuss about two variety of factors, that is two variety of patterns. So one can go for a square pattern or one can go for a triangular pattern. So depending upon the pattern that you are adopting for, then how to calculate the zone of influence, that is capital R. So in case of the square pattern, so the capital R is related to spacing as capital R is equal to 0.564 times of S. While in case of the triangular pattern, it is 0.525 times of S. So S is spacing between two drains. So it is say in square pattern or triangular pattern, so which is immaterial. So from these diagrams, you can also understand what is RD or RW, what is capital R. So this is 2 times of RD means, so this is diameter of the well or the diameter of the drain, and 2R means diameter of the zone of influence, and this is the depth of the sand drain. So this further gives details of the permeability in the horizontal direction and the permeability in the vertical direction. Okay, so these values you must remember, R for square pattern and R for triangular pattern. So these values will not be given in the exam. You must remember. So this is a complete cross section which talks about the zone of influence when it is a sand drain or the PVD immaterial. So this is surcharge load. This inner thing is DC is the diameter of the drain. You can see diameter of the drain. This is smear zone and this is undisturbed soil. Plan view and the same thing in cross section view. KC is the diameter of the drain. KC is permeability of the sand in the drain. KS is permeability of the soil which is in disturbed or smear zone. KV and KR are permeability in the permeability of the soft soil, native soft soil in the horizontal and the radial direction. And DE is the zone of influence. DE is the zone of influence. So these are some more information about suppose in all the situations it is practically not possible to determine the permeability in the horizontal direction, permeability in the vertical direction, the permeability of the smear zone, as well as the consolidation in the vertical direction as well as in the horizontal direction. So different people based on their experience and having analyzed the different case studies, they try to propose a correlations between how to calculate what is the approximate probable diameter of the smear zone or how to relate the horizontal permeability, vertical permeability, and so on and so forth. So here you can see the diameter of the smear zone. So as per Hansbo is approximately 1.5 to 3 times of the diameter of the drain. And Bergado has told it could be up to 2 times of DW. And Indraratna and Redna and Bo et al, Zio et al, so they found that it could be up to 4 to 8 times of DW. Now, what value to be picked up, it is up to our prerogative, but you should understand it is dependent on the soil type. So it's understood that if you look at all these others, they belong to different countries. So meaning thereby, so they are working in a different clay soil type. So depending upon the soil type, the zone of influence might be different. Then similarly, the permeability in the horizontal direction, Ks, that is permeability of the smear zone effect. So this is they say the ratio of Kh by Ks is approximately 2 to 6. So given by many people has told that the ratio is between 2 to 6, but somebody has told that it could be even 1 also. And here this is the relationship between Ks is equal to 1 by lambda into Kr. So this is 2 to 6, both are same. And coefficient of consolidation, including the smear effects, Ch is equals to Cv. So you can assume Ch is equals to Cv. But you can also vary the values. There is no problem. This is the governing equation for the vacuum consolidation. So given by Chu and N 2005 to calculate the average degree of consolidation. So this is some fundamentals about how to understand optimum penetration under vacuum preloading. Suppose if you are applying, there could be formation of the some zone of influence. So then, so this is a drainage. Suppose if you look at the cross section of the PVD improved or vacuum free loading condition. So when vacuum pressure, this is as a function of the depth. So initially US0 and at the bottom of the PVD it is US1. Okay, so accordingly there are the change in the permeability within the zone of vacuum preloading, that is KV1, and below the soil, that is KV2. So this is another equation proposed by Chai et al. To calculate the minimum depth of improvement based on the permeability. So Chai et al. Developed a solution for determining the optimum penetration depth of PVDs based on simplified distribution of vacuum pressure with depth. So when you talk about the vacuum free loading, so we are going to apply the vacuum pressure in order to drain out the water through holes. A number of holes are made. So holes may be in the form of a PVDs. So let us also try to understand some design aspects of the sand drain. Let's try to go in a very systematic way. So these are the few design considerations. The very first one is types and patterns. I have already discussed there could be two variety of patterns, square pattern and triangular pattern. In case of the square pattern, to calculate the diameter of the zone of influence, it can be related to the spacing as dE is equals to 1.13 times of S. And for triangular pattern, the zone of influence, the zone of diameter of the zone of influence is 1.06 times of S for triangular pattern. And there are other factors also, as you can see, depending upon the installation method. So how to select the other parameters? See, this is the sand drain. So installation method was driven or vibratory closed end mandrel. So in this case, the drain diameter might vary from 0.15 to 0.6 meter, and typical spacing 1 to 5 meter, and maximum depth is less than 30 meter. So sand drain. This whole slide talks about only the installation method. So in the earlier it was driven or vibratory closed end mandrel. Now suppose if we use hollow stem continuous flight augers. So if this is the installation mechanism, then what should be the drain diameter and what should be the spacing and what should be the maximum depth? Sand drains by jetted method, then drain typical spacing and depth of installation. So there are two technology normally we use in case of accelerated consolidation. One is sand drains. So this technology is almost obsolete. Now we are more giving preference to prefabricated vertical drains. Those are called as the PVDs or wick drains. So this is a prefabricated sand drain. So this PVD is driven by driven or vibratory closed end mandrel, flight auger, rotary washboarding, displacement or non-displacement. So in this case, the drain diameter should be 0.06 to 0.15 meter, and typical spacing is 1.2 to 4 meter and valid for less than 30 meter. And PVD driven or vibratory closed end mandrel displacement. And this is the drain diameter and typical spacing, and we can go up to 60 meter. So, but if you look at this slide carefully, uh, the effective depth of any sand drain is up to 30 meters. 30 meters. So if you want a little further, then it is preferable to go for PVD technology rather than the sand drain. So I will discuss in detail about the PVD. So then when you talk about the PVD, the accelerated consolidation, So we normally implement this sand drain on a weak soil where the bearing capacity is a problem. So in that case, how to calculate what is the minimum bearing capacity offered by the clay material? So you can use this equation where P is equals to Q ultimate by factor of safety. Since you are dealing with the clay, so this is N bearing capacity factor divided by Cu by factor of safety. So this will give you, depending upon the value of the cohesion, what should be the minimum bearing capacity that the soil is offering. Then accordingly, we can decide what should be the minimum surcharge height that we should put, so that that particular soil will not undergo any kind of the slope failure because of the induced settlement. Because this is one of the most important factor when you try to deal with the sand drain technology in a soft soil. If you do not understand the minimum bearing capacity, then you may end up in most of the times with the slope stability failure. Okay, and this slope stability occurs so like a base failure, because you have a soft soil that is exist in the natural condition, and on top soil you constructed an embankment, but the embankment is a compacted one, but the bottom soil is under undrained condition without any compaction, and the soil is under undrained condition. So when it is undrained condition, the strength is quite less. So because of the less strength, so it may allow to undergo huge amount of the consolidation, which ultimately resulting in slope stability failure. So therefore, before you go for implementation of PVD technology, you must analyze, is there any possibility of the slope failure because of the imposition of surcharge load. You can use any method. So if slope stability becomes a problem, then what should we do? So then we should go for geosynthetic reinforcement or other ground improvement methods that can be used to stabilize the embankment. By no means you should allow the failure to occur within the soil or within the embankment. Then another important factor is how much time is required to achieve the desired degree of consolidation. So you can use the degree of consolidation theory for instantaneous load with no vertical drain. So Terzaghi's 1D theory. For linearly increasing load followed by constant load, so use Taylor and Olson approach. These are different theories, their validity. With PVDs, Hunsbo solution or the equivalent permeability method. Okay, so for different conditions, so people have recommended different kinds of the theories. The first is use consolidation theory. If it is instantaneous load with no vertical drain, then go for Terzaghi's 1D consolidation theory. If you are a ramping load is a ramping loading, that is the load is increased linearly followed by the constant means you are stopping, then try to use Taylor's equation or Olson's approach. So in case instead of the sand drains, if you are using the PVD, then go for Hunsbo solution, or alternatively use equivalent permeability method for calculating the time for consolidation. So these are equations given by Olson, so 1977. So solutions for 1D consolidation. So for this is a ramp loading or instantaneous loading. So this is one important thing is since the beginning of this ground improvement technique by sand drain technology, we were talking about the accelerated consolidation. Now, when I say the consolidation, it is obvious that we are anticipating huge amount of a settlement, but it is only the settlement that is happening without improvement in the soil strength, or will there be improvement in the soil strength as well? So when you are improving or inducing the more and more settlement, there is a change in the over consolidation ratio. So accordingly, they try to correlate what should be the improvement in the cohesion value as and when the consolidation is progressive. So this is the equation proposed by the LAT. As you can see, the Cu is equals to, or Cu by sigma z dash is equals to chi f into OCR power. So Cu is undrained shear strength of saturated cohesive soil, and chi f is this is the factor. So it can be taken between 0.2 to minus 0.03 for homogeneous sedimentary clays to better understand what they are meaning. So if it is falling above the A line of plasticity chart, and chi f is equals to 0.25 plus or minus 0.05 for silts and organic clays, or where that particular soil is falling below the A line of plasticity chart. OCR is over consolidation ratio. So this is a cap. So the another form of equation of this notation is 0.88 into 1 minus CR by CC, where CR is recompression index, CC is compression index, and sigma naught sigma dash Z is effective consolidation stress. So here we know how much amount of consolidation or the excess pore water surcharge load is applied, and OCR you need to calculate over consolidation ratio. Since from the consolidation theory, if you draw the wide ratio versus the applied load, then we will get, based on the slope, the value of the CC and CR, coefficient of consolidation, and the coefficient of reconsolidation or coefficient of rebound, recompression index, whatever it is. So once I know all these things, and depending upon the soil type, I can pick it up either 0.22 or 0.25. Then after decide to calculate what is the improvement in the undrained cohesion value of the soil sample. So this is how you should calculate improvement in the strength after desired degree of consolidation. Okay. So this is a same strength gain equation given by the different people, and further information, the strength gain of the soil after consolidation, delta Cu is equals to chi f into OCR power 4 into same equation. Some more information, since soft soils are often approximately normally consolidated, so where OCR is 1, chi f can be taken as chi can be taken as 0.25. So when the width of the load area is much larger than the thickness of the soft soil, so then you can say delta Cu is 0.25 times of UT into P. So where P is applied uniform pressure for preloading, and UT is average degree of consolidation. UT is average degree of consolidation. This is degree of consolidation at time t, calculated from the previous step. So this form of the equation is same as this form of the equation. Okay, for different conditions. The condition is when the width of the load area is much larger than the thickness of the soft soil. Then the total undrained shear strength, how do you calculate? So Cu1 is equals to the initial cohesion plus the improved value of the cohesion. Initial one plus the improved one. And settlement calculation. So the settlement at any time t is nothing but UT into the SF. You can see the settlement calculation. The settlement at any time t is nothing but the degree of consolidation at that time multiplied by the total settlement. So this slide will give you information about how to calculate the improved cohesion value and how to calculate the settlement at any given time for that particular degree of consolidation achieved. So this is surcharge effect. If we want to take the surcharge effect into for calculation of the degree of consolidation, we can use this one, time for surcharge removal, because if you look at this graph, we have taken some amount of the time for applying the surcharge load, and the same load is maintained for some time. and we also remove the certain amount of the surcharge. If you look at carefully, the difference between the maximum applied surcharge load and PF is that PF means, so this is the amount of the load might come because of the construction of the superstructure. PS means the additional load removed in the form of a surcharge load. So this is applied pressure versus time lag. And if you want to account for this removal of the surcharge load, then we can determine another factor, that is the effective surcharge ratio, which is defined as sigma dash ZS divided by sigma dash ZF. So ZS is the amount of the surcharge removed, ZF is the amount of the surcharge that can exist. So minus 1. Sigma dash ZS effective vertical surcharge stress in the soil before removal of the surcharge, and sigma dash ZF the final vertical stress in soil after removal of the surcharge. So the ratio between these two is defined as the effective surcharge ratio. So this is because of the various reasons. So what will happen to the vertical stress condition in the soil? So with imposition of the surcharge and upon removal of the surcharge, and this is the condition for excess pore water pressure, and this is the condition of the settlement. As you can see, excess pore water pressure, as you are increasing the load, so there is an increase in the excess pore water pressure. When the surcharge is maximum, there was a maximum increase in the excess pore water pressure. And when you try to maintain the surcharge load for a prescribed period until such that the entire excess pore water pressure gets dissipated. And when you remove certain amount of surcharge load, and obviously it reflects in the form of a decrease in the excess pore water pressure. Initially it is positive, then it goes to the negative, and upon construction of the superstructure, again it comes to some rebound. That is the initial value. So you can see there is a small rebound in the excess pore water pressure. However, it is so negligible, but it could never achieve the initial excess pore water pressure. Okay, that means the consolidation has fully occurred within this soil mass. Similarly, there is a changes in the settlement. You can see as you are inducing the surcharge load, so consequently there is a progress in the settlement. As you can see, there is a continuous decrease in the continuous increase in the settlement. And when you try to remove the surcharge load, you can see some kind of a rebound in the surcharge. So as we have seen in the previous slide, how to calculate the CR and how to calculate the CS, so that can be understood from this graph. So this is another form. So to prevent the continued primary settlement after the removal of the surcharge, so the achieved degree of consolidation should be equivalent to this minimum value. So PF, so as you can see, this parameter is the surcharge load after the superstructure construction. PF is vertical applied pressure after removal of the surcharge, and PS is vertical applied surcharge to be removed. So this is another parameter. This equation should be used to calculate the achieved degree of consolidation. So then accounting for the surcharge effect, then how do you calculate the primary rebound or the settlement accounting for the rebound? So this equation you can use it. SR is equals to CR into H by 1 plus E naught. You can compare this equation with the primary consolidation settlement equation, that is SE equals to CC into H by 1 plus E naught into log sigma naught plus delta sigma by sigma naught. But since you are dealing with the surcharge loading conditions here, so we can embed those changes in surcharge conditions in order to calculate the rebound settlement SR. So using this simple equation. So this is some demonstration about how to understand whether we have achieved the desired degree of settlement or not. So you can see this is the real-time monitoring data, so given by some people. So from the above 0 we can understand the height of the fill, and below 0 it indicates the progress of the settlement. So initially there is a small amount of the surcharge load maintained for some time. Then there is a ramping of the load maintained for some time. So there is another ramp of the load maintained for some time. Then the final ramping. And the same load is maintained for certain time. Now the question is how long the surcharge load should be maintained, or what should be the elapsed time of surcharge load, so that we will achieve the desired degree of consolidation and at the same time with the desired amount of the settlement. So that can be ascertained by constantly monitoring what is happening to the settlement. Ultimately the final settlement supposed to become constant after certain time. Okay, so if you look at these relationship carefully, after approximately 8.5 months or 9 months time, the settlement started becoming almost constant. And in fact, you need to monitor even behind the elapsed time. So would there be any kind of a recovery in the settlement, or the same settlement is continued even after removal of the surcharge load for some time? Okay, as you can see, there was a small rebound. But thereafter it became almost constant. Okay, so this one needs to ascertain after removal of the surcharge load. If there is a possibility of the huge recovery in the settlement, so it is not advised to go for construction of any superstructure on it, or you are confirming that there is no problem with the soil even after subjected to ground improvement. So this is one way of confirmation and ascertaining. So this is by simply monitoring the settlement. So this is typical soft soil profile. So where the ground improvement was done by the sand drain. So this is elevation below the ground. This is the soil profile. There is a muddy clay, there is a mud, and there is a silty clay. So all are soft soils. And on this soil, the sand drain technology has been implemented. And the same thing is monitored in the form of a settlement and in the form of a pore water pressure. You can see. So this is the measurement of the pore water pressure. So this is the sand drain. So what is happening to this is excess pore water pressure at the end of the filling. We can understand that this is the initial condition of the excess pore water pressure. That means when you apply the load, the whole load is borne by only the water molecules, or only by water. So this blue line indicates the load borne by water. Now because of the surcharge load, the water starts dissipating. Okay, so consequently, so there is a dislocation of this blue line. So that is again in the form of a black line, as you can see. So there is a decrease in the excess pore water pressure. So this is after half a year of preloading condition. Then if you maintain the same surcharge load even behind 6 months, there is a further reduction in the excess pore water pressure, as you can see. Now another important point also you can observe is so this is the bottommost point of the sand drain. So above there was a huge change in the pore water pressure condition, but below there was no change in pore water pressure condition at all. Okay, so that means whatever the depth up to which the sand drain has been provided, so it can dewater only that particular zone, or it can accelerate the consolidation only in that particular zone. Okay, so in the previous slide the changes in the ground was monitored in the form of a settlement. But in this slide, the changes in the ground were monitored in the form of a pore water pressure. Okay, so and this pore water pressure can also be related to the settlements. Either way, it is all right. And at the end of the day, the calculation of the settlement based on the pore water pressure and direct settlement calculation both should match. So this is a schematic of the sand drains. So this is earthen fill. These are all sand drains, and this is the soil profile. So this slide gives a typical installation of the sand drain with surcharge loading. So this already we did discuss. This is not required. So this is what all about the sand drains. So I can take a couple of questions before I begin the PVD.
Sir,
Yeah.
and exact can be calculated like before we did by Diaplonia in this vibro float. Here is some
Yes.
trick also.
Yeah, we can calculate. I will take the tutorial on this one completely.
Okay, sir.
Okay. Next two classes will be only tutorial on sand drains. Yes, please. Any questions? Hello.
Sir,
Yeah.
sir, in one of the slide you showed that in the zone which is not influenced, means after the smear zone, the undisturbed zone which we are having, we have
Okay.
the consolidation in both the direction, horizontal and vertical.
Correct.
In the smear zone, it was shown that it is only in the horizontal direction,
Yeah.
and in this where the well is there it's shown in only the vertical direction.
Correct.
But is it exactly true? Means it will be in both the direction in all cases, na?
Usually yes, but see, our primary aim is, suppose if you look at this diagram, so this is a sand. This is sand drain where permeability is very high. What should be the core function of this sand drain? Whatever water is coming from the native soil or the soft soil, say from the horizontal direction or the vertical direction, it should pump in the vertical direction. Okay, and for sand, there is nothing like the horizontal permeability or vertical permeability. It will be same in both the directions. Okay,
Okay, sir.
so that is for the sand. And for clay, the horizontal permeability is different than the vertical permeability. But for smear zone, actually, in fact, the thickness of the smear zone is so small, there is no point in trying to distinguish between the horizontal and vertical permeability. Okay, its thickness is very small, a couple of centimeters might be. So that is the reason we don't accord any importance to the permeability in the horizontal and vertical direction of the smear zone.
Okay, sir.
Yeah, any other questions, please?
Sir,
Yeah.
sir, how will we identify the type of failure in sand drain?
How will you identify? So this is a very tricky question. uh, should be some techniques to confirm alignment. I also do not know exactly. One thing is we will come to know whether they are working or not only the post imposition of surcharge load. Okay, that is certain. In case of the pile foundation, we have we can do the pile integrity test whether it is in a vertical direction or not. In case of the sand drain, I don't have any idea whether only thing is if it doesn't work, then we should ascertain that there was some problem in the sand drain. It is really difficult. It's not so easy.
Sir,
Yeah.
will groundwater affect the functioning of sand drain?
Groundwater, it will not affect because when we try to implement the sand drain technology, the soil is already under fully saturated condition. And when we impose the surcharge load, so it tries to dissipate the water from that particular location. And by then the groundwater tries to return it. So I get the soil is already consolidated. And soon after the consolidation, we will go for the superstructure construction. So even if the groundwater returns, since the consolidation has already happened, so there is no problem as such.
Okay,
Because
so in this
suppose,
diagram,
yeah,
in
if you do, there are two important things you need to understand. The seasonal changes of the groundwater without surcharge load and the effect of seasonal changes of the groundwater after the surcharge load. You might have heard of self-consolidation. When you talk about the 1D consolidation, self-consolidation means consolidation because of their own weight, not because of the surcharge load, because of their own weight. So when self-consolidation is happening, that may be typically attributed to your groundwater influences, because when there is a rise and decrease in the groundwater, there is a change in the effective stress condition. So this change in the effective stress condition triggers the consolidation very slowly, very slowly. So that's why wherever you see any kind of a clay soil, so they undergo settlement continuously, but in very slow magnitude. That's because of the self-weight consolidation and because of the changes in the groundwater conditions. But when you impose the surcharge load for a particular time, I don't think so, because that effect is already nullified. The changes in the effective stress condition, total stress condition was already nullified. So even if the groundwater table rose to the ground surface, there will not be any effect.
okay, so groundwater table can rise after consolidation.
Yes, yes, yes.
Okay.
Yeah, any other questions? Okay. So let me discuss about the another one which is most widely used, and you supposed to know about this technology more importantly. I will talk about how this technology is different than the sand drains, because the design philosophies remained same between the sand drains and the prefabricated vertical drains. Both are same. There was no any difference in the design philosophy. But in terms of the geometry, in terms of the material, there is a huge change between the sand drain and the prefabricated vertical drains. So here the bottom right side, a simple schematic has been given. So this is called as a prefabricated vertical drain, typically called as a PVD. So it has two core components. One is the geotextile fabric, as you can see here. This is geotextile fabric, and next is called as a core, polypropylene core. So this the two main attributes of this fabric and core is that the fabric is like a geotextile. So it has a lot of pores and it will act like a non-returning valve. It allows only water to infiltrate from the soil into the core, but it will not allow the soil particles to plug or permeate through these pores. That is the function of the geotextile fabric. Now, if you look at carefully this polypropylene core, this is manufactured for a particular geometry. As you can see, there are some vertical stands between, and there is some space between these vertical sand. You can see there is some kind of formation of a channel C type on either side from the central. So these channel C types will act as some kind of the capillary tubes. These will act as capillary tubes. So through this capillary tube, the water comes to the ground surface. Now from where the water is ingressing, through the geotextile fabric. Since this fabric allows only the water but not the soil particle, so therefore only water allows into the core, and because of the capillary action, so from wherever it is penetrating into the fabric, and because of the capillary action, it comes to the ground surface and gets collected over there. So this is all PVDs are manufactured for a particular geometry. Typically, as you can see, there are two geometrical parameters, A and B. So A is width of the PVD, which typically ranges between 95 to 100 millimeter, and B is the thickness of the PVD, which typically ranges between 3 to 5 millimeter. And this geotextile is wrapped all around the polypropylene core, wrapped all around. So this is the fundamental definition. PVDs which are inserted into the soft ground provides additional drainage path for accelerating the consolidation of fine grained soils by promoting the radial drainage. Now, unlike the sand drains, the permeability of this core is much higher than the permeability of the native soil. So therefore, even when you are going for the PVD technology, we are still maintaining the contrast in the permeability value between the soft clay and the PVD. So they are also called as wick drains or strip drains or PVDs. All are synonyms. We can use any terminology, so there is no problem. So this is another cross section. So this is 120 millimeter width, 60 millimeter width, and 8 millimeter thick. As you can see, these are all channel types. They will act as some kind of the capillary tubes, and outside geotextile is wrapped, and this is a real picture. This is a plastic core and this is filter jacket. So these are the two functions. Central core function is primarily to act as a free drainage channel to allow the water from at any depth to the ground surface. Then non-woven filter jacket function is allows water to flow in. So this is the function of the non-woven filter jacket and the function of the central core. So the installation of the PVD is very similar to installation of the sand drain, but here we don't need to make any borehole. In fact, the installation of the PVD is much faster. It hardly takes a couple of minutes. So these are some real life pictures where PVDs were installed, as you can see. So all these outcrops are PVDs, and this is the mission which is driving the PVDs into the desired depth. And this is the sand blanket. This is sand blanket, and you can see there are two things. These are individual strips. This is an individual strip. All these are individual strip. And also look at, there is another pipe which is interconnecting all the PVDs. So whatever the water that drains from below the ground surface to the ground surface through the PVD, it will again enter into this black channel, this black pipe. And these black pipes are channelized to sump. So therefore, from all the different PVDs, whatever the water comes out below the surface will be collected in a sump, as you can see in this picture. So this is a specific network that is followed to dewater and thereby accelerate the consolidation of soil. And you can also see the spacing between, see for example here they followed the triangular pattern. So they followed the triangular pattern. So anything you take it. So this is the drill machine that is used to install the PVD. It's a very quick process. This is the mechanism of the installation. So this is the original ground. So when you want to install the PVD, the end of the PVD is folded, and it is folded with some iron piece. With some iron piece or anchor plate, as it means shown. Folded and attached to one anchor plate, and this anchor plate is permanently left inside the ground. So this is the original ground, and you insert the PVD to the anchor plate in a next step, and PVD along with the anchor plate is driven into the ground up to the desired depth. Once it has been driven or installed at the desired depth, the PVD at the ground surface is simply cut at the ground surface. It is cut at the ground surface. That's it. That is simple installation. Now, how it is retained inside the ground, you can understand, because there is a mandrel, that is the drill bit to which the PVD and the anchor plate are attached. Okay. So if you don't attach, then you can't able to penetrate the PVD, because when you are penetrating the mandrel, so even PVD also has to penetrate. But when you are retrieving the mandrel, there is a possibility that the PVD also can retrieve. So therefore, we need to leave the PVD at that location only. In order to do so, it is attached to the anchor plate. So when it is installed to the desired depth, this anchor plate, this is during the penetration, and upon left, when you are retrieving the mandrel, this anchor plate, so it is attached to the soil adjacent, and this soil simply flows in and develops some kind of the passive earth pressure. So because of this passive earth pressure, the anchor plate is left inside the ground along with the PVD. Only during the retrievation of mandrel itself only comes out. So this is the simple mechanism of installation of PVD. So meaning thereby, I need one anchor plate during the installation of one PVD at one location. Okay, suppose if you look at this one, so numbers of PVD has been installed. So I need so many numbers of anchor plates. Okay, so this is the mechanism behind use of anchor plate attached to the PVD and installation of the PVD. So these are some important points about the PVD. Installation of PVD is typically 6,000 linear meters per day and result in the lower project cost. If we compare the installation of the PVDs with the installation of the sand drain, so up to 6 kilometers running length of PVDs can be installed in a day. But if you, in case of the sand drain, it is hardly a couple of meters, maybe double digit or maybe triple digit. Such is the variance between the PVD installation and the sand drain. So no risk of PVDs breaking during installation because these are the plastic materials. So you can ensure that there is no breakage of the PVDs at all, which is a typical case normally we encounter in case of the sand drains. No risk of shear failure of the PVD during the settlement. Sand drains are vulnerable to shear failure during the settlement. In fact, this is a plastic material. If at all there is a lateral thrust within the soil sample, this PVDs being a plastic materials can offer some kind of the resistance to the lateral thrust. That is some additional advantage. So PVDs have high discharge capacities, typically 30 into 10 power minus 6 cubic meter per second to 19 to 10 power minus 6 cubic meter per second. So compared to a 350 millimeter diameter sand drain with a discharge capacity of 20 into 10 power minus 6 cubic meter per second. So this is some typical comparison. You can also understand. So when you are installing the PVD, the geometry is quite small, 100 millimeter width and 5 millimeter thickness. But if you look at the sand drain, it is hoping 350 millimeter diameter. You can imagine how much sand is required if you are installing a 350 millimeter diameter sand drain up to a depth of 30 meter. So pi by 4 into 350 square into 3000. So this is the volume of the sand that is required to finish one sand drain. But in case of the PVD, you simply require only some plastic tube. When installed with the purpose designed mandrel, smear effects are much smaller for PVDs than for the large diameter sand drains. So this is another important observation made by different people. So the smear zone effect is much smaller in case of the PVD as compared with the sand drain. So PVDs are consistently factory produced, whereas sand drains are subjected to quality variance of natural occurring sands. So this is also another important point. And maximum flow observed from PVD is 5 into 10 power minus 6 cubic meter per second. So that is 150 cubic meter per year. That means this much amount of water. So they can dewater from the soil sample in a year. It's a huge quantity. So with hydraulic gradient approximately of 0.1. However, there may be some factors that can affect the PVD performance, which include reduction in the discharges from due to deformation and creep of filter into the core. That means if geotextile is because of its soft nature, if it blocks the core of the filter, so then there is a possibility of decrease in the discharge capacity of the PVD. Permeability reduction due to clogging of filter and core. So it is obvious that the soil particles are different. These are non-homogeneous. So we cannot say that there was no plugging or clogging of the geotextile. There could be possibility. So it may not happen instantaneously, but with time it is bound to happen. So therefore, whatever clogging that should happen with time, so it may obviously reduce the permeability. It may reduce the performance and overall efficiency of the PVD. Bending and kinking of PVD during settlement. So try to also recall when we talk about the accelerated consolidation, the envisioned settlements are in terms of the meters. So meaning thereby the PVD which is installed should also undergo equivalent settlement. When it is going, then we can expect some kind of bends and kinks in the PVD. But that bending and kinking action should not affect the overall performance of the PVD. So then pressure on the PVD. So PVDs are the soft materials. They can't able to take any amount of the pressure coming in the axial direction. So these four factors might affect the overall discharge capacity of the PVD. So therefore, when you design the PVD, so take into account for these four important features. And how to calculate the discharge, that is volume by hydraulic gradient. So this is Darcy's law, and the value of the Q dash should be greater than 140 as per the ASTM code. The minimum discharge should be greater than 140 into 10 power minus 6 cubic meter per second. So this one has to measure of the PVD. So this is a discharge capacity of the PVD. Okay, if it is below than this, so that PVD should be discarded. So this is the simple graph which gives some understanding about how to calculate the discharge capacity. So this is discharge Q versus for different hydraulic gradients. So the slope is nothing but QW, maximum, the actual gradient. Okay, so based on this graph, we can decide what should be the minimum hydraulic gradient that can be maintained. In case of the sand drain, we have directly taken the diameter of the sand drain as the zone of influence. But in case of the PVD, so we don't have a circular geometry. Rather, there is a PVD with a particular width and particular thickness. So therefore, how do you convert the width and thickness into the diameter? So different people have suggested different equations as shown in this slide. You can see dW can be calculated as 2 into W plus T by pi. This is the width and this is thickness. W is the width, T is the thickness. Or somebody has suggested simple perimeter by one side half of the perimeter by 2. And somebody suggested dW is equal to 0.5 W plus 0.7 centimeter T. So these are the different equations. In fact, more number of equations are available to calculate the equivalent cylindrical shape from the width and thickness. So these are the some more equations. Equivalent diameter of a PVD based on perimeter equivalence and considering a correction factor. So that is DC is equals to alpha D into 2 into B plus TG by pi. B is width and T is thickness. Alpha D is a correction factor which is typically 0.9 to 1. But in order to avoid some kind of confusion, Federal Highway Administration has given some kind of the guidelines. You simply take B plus TG by 2. That's good enough. Then some other guidelines when you go for the PVD installation, the minimum discharge capacity of the PVD should be calculated and ensure that it is greater than this one. The required discharge capacity of PVD is QC is equal should be greater than or equals to 7.85 times factor of safety into KR into H square, where QC is a required discharge capacity of a PVD. Okay, so this required discharge capacity to be ascertained before these PVDs are installed at the ground site. FSC is factor of safety, typically 4 to 6. KR is radial permeability of the soil, and HDR is maximum drainage distance of PVD. So that is D by 2, DE by 2. In fact, if you take the zone of influence, it is half the zone of influence is called as a HDR. So since there is a possibility of the clogging and plugging, so then accordingly you should ensure after what time there is a possibility of the clogging. So to ascertain that one, then we need to use some kind of the filter criterion. So to understand the soil retention for geotextile filter to meet the soil retention criteria and drainage and clogging. So this is O95 should be less than or equals to 2 to 3 times of D85. So D means diameter of the particle. O means apparent opening size of the geotextile. You can see O95 apparent opening size of the geotextile filter should be less than or equals to 2 to 3 times of the diameter of the particle corresponding to 85%. 85% is final. And similarly, O50 mean opening size of the geotextile should be less than or equals to 10 to 12 times of the mean diameter of the particle. So you need to ensure that O95 is less than this value and O50 is less than this value, so that in the near future the PVDs will not clog and thereby will not impede the drainage properties, and we can ensure maximum performance of the PVD. And the drainage criteria for geotextile filter. So the permeability to the PVD must be greater than or equals to 10 times the permeability of the soil. Well, in case of the sand drain, it was almost 1000 times. And this is a clogging criteria for geotextile. The porosity of the filter must be greater than 30%. And O95 apparent opening size of the geotextile filter should be greater than or equals to 3 times 15 is soil particle size corresponding to 15% of percent final. And another important O15 should be greater than or equals to 2 to 3 times of average particle diameter, that is D10. So there is another concept that can be used, because normally we input the permeability in the horizontal direction and the permeability in the vertical direction so as to calculate the overall degree of consolidation. But there was another concept that is called as the equivalent permeability. So suppose if you know the horizontal and the vertical, the everything can be converted into equivalent permeability. So taking the entire soil as a single zone. So that is now your entire soil zone is represented with equivalent permeability and the corresponding depth. That is the depth up to which PVD is installed. So this is the equation proposed by Kai et al. So equivalent vertical permeability, which accounts for both horizontal as well as vertical permeability, be it found, and other factors also. And f of m nd is a function, so same as that proposed with Ansbo. So without accounting for the smear zone, with accounting for the smear zone, everything we can take into account. And these are
Sir,
yeah,
sir, when we will consider this equivalent permeability,
yes,
then we will not, it's for all, whole soil without considering this PVDs also.
yeah, of course.
Okay, sir.
So this is the some how to calculate the equivalent diameter dW in case of the PVD, that is 2 into A plus B by pi, and how to calculate the average degree of consolidation due to radial drainage, the same equation. So that we have seen in case of the Barron's equation. So this is alpha dash. So this accounts for both smear effect as well as well resistance. And so this is the relationship between degree of consolidation versus time factor. Either you can use the predefined chart or you can use this table. And these are some more equations. TR dash time factor for radial consolidation, CVR into T by dW square. The TR dash in another form, that is relating with the alpha dash and average degree of consolidation. So alternatively, we can also use these predefined charts to pick up the values of n, where n is the ratio of dE by dW, that is equivalent zone of diameter by drain diameter, n, and alpha dash is a constant. Alpha dash is a big equation. Or solving this entire numerical equation, so we can simply use this chart. This is alpha dash, this is n, and as a function of s is it is the ratio of the diameter of the smear zone by diameter of the drain, and kh by ks, the ratio of permeability in the horizontal direction to vertical direction. So for different values of and here also we can go for either triangular pattern or a square pattern, same equation. So a relationship between the zone of diameter versus spacing. For triangular it is 1.05 times of S, and for square it is 1.128 times of S. Very similar to sand drain, there is no difference. So this is understand about the PVD. In fact, the PVD is a rectangular geometry with width A and thickness B, but that is converted into equivalent diameter, that is dW. Then there is a, this is small inner circle. Then there is a zone of influence, that is called as a smear zone, and the overall zone of influence, that is equivalent diameter. So this is the equation to use to calculate time required for certain degree of consolidation. Certain degree of consolidation for particular time. So these are the different steps the design of PVD. You can go through it when I share the slides. And these are some assumptions in Barron's theory of this. I did not discuss during the sand rains, but these are some assumptions. You can also see when I share the slides. And these are the equations. Earlier we were knowing directly the diameter of the sand rain, but in this case you need to compute the value of the equivalent diameter. Then equation for computing the average degree of consolidation. This is function of n. The function of n accounts for this is for a perfect drain, and taking into account of smear effect, taking into account of well resistance, so on and so forth. This is for a perfect drain. Then time factor for radial consolidation and definition of the n value. And this is a predefined chart relating the degree of consolidation with the time factors, valid for both vertical as well as the radial. This middle for vertical consolidation, and remaining all thick dotted lines or the thick dark lines are valid for the radial consolidation. So these are the equations which have been derived. Again, to calculate the average degree of consolidation because of both vertical drainage as well as the radial drainage. So this chart we can directly use to calculate the average degree of consolidation because of vertical as well as the radial, and because of the time factor TB. So this is a model very similar to sand drain, which depicts the central core is the vertical drain, and there is a smear zone effect, and there is an undisturbed clay. So this is equation accounting for the smear effect. KH is the permeability in the horizontal direction. KS is permeability of the smear zone. Then accounting for smear effect plus well resistance or only smear effect, and for perfectly only smear effect. Yeah. Then some more information about how to pick up the values of the area of the smear zone. AS is equals to 1.6 times of the cross-sectional area of the mandrel. Somebody has tried to determine. Then the ratio of the horizontal permeability by the permeability of the smear zone, approximately 2 as per the Terzaghi. Then coefficient of horizontal consolidation. We can also correlate the CH with CV in the form of the permeability. So then these are the design steps we can follow. These are the different design steps. You can go through it. So this is the equation accounting for well resistance and smear zone, F of L. Okay, yeah. So there is nothing major distinction between the PVD and sand drain except their fundamental materials used. So in terms of the equations, there is almost no changing. So this is all about the sand drain technology. So if you wish to ask any question, you are most welcome.
Sir,
Yeah,
sir, the smear zone which is formed in PVD is will be less than that in the this sand drain.
correct.
Okay.
So there is an important announcement. I'm planning to take some additional classes on this coming Saturday from 10 to 12. Will it be okay? Because we have only, I think, how many classes remaining? How many classes are more remaining? Tomorrow and Friday, I need it only for tutorial and sand drains. Then I have to cover stone column. There also, it is also big huge chapter. At least 2 theory classes are required for demonstration purpose, and 2 classes are required for tutorial purpose. Minimum 4 classes are required. So could anybody tell me how many classes more we have? Today is 24th. Thursday, Wednesday, so 25th and 27th. So I'll be going to take tutorial. Then again we have first, second and fourth. So we have to move. Okay, fine. So I don't need to take any extra class.
Sir,
Yeah.
sir, I had an issue regarding that presentation.
What kind of an issue?
Sir, actually last week I was absent in all the ASLM